Hello. This video, we're going to talk about the seismology, which is a little bit about the science behind earthquakes, but we're going to look at it for what's most useful for engineering work. So let me switch over and start our slideshow. So I want to talk about seismology, which is basically the field of science that deals with earthquakes and vibrations of the earth. But we're not planning to be scientists, we're planning to be engineers. But there's some terminology we probably need to be familiar with, and just the basic science of what's occurring when an earthquake strikes. As an example, I'm going to use some information that was collected after an earthquake in Italy in 2016. It was a sizable earthquake. It definitely was in the news. There were 300 fatalities that occurred in central Italy. And we're going to learn some of the terminology and how to use this one example for illustrating some of it. First off, a couple of terms we deal with is the hypocenter and the depth. The hypocenter is actually the location of the earthquake in 3D space. In other words, it's actually somewhere down in the below the surface of the earth. So the hypocenter is that three-dimensional point where the earthquake is centered. The focal depth then is defined as the distance the hypocenter is below the Earth's surface. Earthquakes occur throughout the solid portions of the Earth, but in engineering, we're mostly talking about what are known as shallow earthquakes, which means the focal depth is less than 100 kilometers, so they're relatively close to the surface of the Earth. Earthquakes that occur deeper than 100 kilometers really have very little chance of damaging anything up here on the Earth's surface, just because the energy they release is going to be dissipated long before it reaches the surface. Now, what most of us are more familiar with is the fault lines. And as scientists look at earthquakes, we generally see that the hypocenter of those earthquakes often occur along lines along the surface of the earth that we refer to as fault lines. So here is the fault line that runs along the eastern edge of Italy. And as you can see, it kind of divides the land of Italy from the water in the Adriatic Sea next to it. The other term that we're probably more familiar with is the epicenter. The epicenter is the point on the Earth's surface that's directly above the hypocenter. So it's really the point on the outside of the Earth's surface that the earthquake occurred directly below. And in the map, it's shown as a star. As you can see, that the epicenter of this earthquake is not on the fault line. Whether the fault goes directly downward or not, oftentimes they slope, and so the earthquake underneath the ground may show an epicenter actually quite a distance away from the fault line. Now, of course, as engineers or scientists, we look for ways to measure earthquakes. I'm going to talk about three common methods, especially, and talk a little bit about how they relate to engineering: the magnitude, the intensity, and the peak ground acceleration. The magnitude is a measurement of the energy that's released during the earthquake. It's a quantitative measurement, meaning that It ends up with a specific number that scientists are generally going to agree on after the earthquake occurs. Most of us are, this is probably the thing that the general public is most common with, is the magnitude, which is often reported on the Richter scale, which was a scale developed by a faculty member at Caltech, Charles Richter, in about the 1920s. The reality is seismologists and geologists no longer use the Richter scale. In fact, the official item now is known as the moment magnitude scale. It's a newer, more accurate scale used by science, but the values are similar to the Richter scale. It just, back in the 1920s, Professor Richter didn't realize how big and how large a magnitude some earthquakes would actually be. About the magnitude, it provides a single number to measure the earthquake. So in other words, an earthquake occurs and the scientists come to a conclusion that that earthquake had a magnitude of 7. The bigger the number is, the larger the earthquake. One thing to keep in mind is that an increase of 1 on this scale means approximately 30 times more energy. Technically, there's no maximum for this scale. In other words, we can always have a future earthquake, which is even a larger magnitude than has ever occurred before. But some examples, the Loma Prieta earthquake of 1989 in the San Francisco Bay Area was 6.9. The Tohoku, Japan earthquake of 2011 that caused the tsunami was 9.1. Chile had a devastating earthquake in 1960s, the largest recorded so far, with a magnitude of 9.5. The epicenter is directly above the hypocenter, usually reported then in longitude and latitude, and then assigned to this earthquake was a magnitude of 6.2, certainly a noticeable earthquake, but certainly far from the largest earthquakes that can occur around the world. The second measurement I want to talk about is intensity. Intensity measures the effect of the earthquake. So it's not so much how much energy is released, but how much effect will that earthquake have, mostly on the human environment. And one thing is, it's a human judgment used to calibrate on a calibrated scale. What that means is that rather than having a specific quantity to measure, it's a more qualitative judgment. And it's certainly possible that two leading experts may give a different level of intensity for the same earthquake in the same location. The most common measurement of intensity for almost everywhere in the world is known as the modified Mercalli scale, and there are 12 levels. It's a subjective value, so one person may give this a certain level, another person may give it a different level, but obviously they'll probably be rather close together. It's useful for government response, insurance, estimated financial impact. It's of less value to working engineers, but it is commonly referred to, and we probably want to at least be familiar with the idea. Now, when we talk about intensity, we actually get multiple values for the same earthquake. In fact, the closer you are to the epicenter, probably the more impact that earthquake has. And so you would get a larger reading on this scale. After an earthquake, what we often see is what's called an isoseismal map, which literally are contour lines of regions that have the same intensity reading after this earthquake. They tend to all center about the epicenter, but as you get further away, the intensity starts to drop off. What are some of these levels? Well, for example, level 8, intensity is usually referred to in the Roman numerals. Level 8 is known as a severe earthquake. What the definition? Damage is probably going to be slight in specially designed structures, but there's probably considerable damage in ordinary buildings, and poorly built buildings are going to perform quite poorly. What does this look like on the field? This is an example of that Italian earthquake with the level 8 damage. As you can see, a lot of partially collapsed buildings. If we look at an aerial view, here's that clock tower. As you can see, some of these buildings are completely collapsed. Many of them have severe damage, but on the other hand, some buildings are still in quite good condition. As you close in a little more, you see the complete collapse of several buildings on several blocks. But as I said, some buildings still look like they have had rather minimal damage. Partially, walls have collapsed. Some buildings relatively undamaged. If we go into that neighborhood, we look at masonry construction. Here's a stone block wall construction masonry. It's got a rather relatively heavy timber floors and roofs. It's not really the way we build structures today, but obviously in countries like Italy, there are still many structures that use blocks without any bonding mortar. That can be compared to masonry construction, which is made of clay bricks for the walls, wood beams, floor framing. This building looks like it's newer construction, but it's probably still older than me, so it certainly is far from modern. But these are masonry blocks with bonding mortar, but it doesn't look like there's any reinforcing steel being installed in these walls. As we move further away from the epicenter, now we get to a level 6, which is a strong being felt by everyone. A lot of people are going to be frightened. Heavy furniture is moved around, but slight damage to structures. Level 5 would be moderate. It's felt by nearly everyone who's awake. Maybe you get some broken windows, but relatively little impact. Level 4 would be felt if you were indoors, but to reality, it may feel much different than a heavy truck driving by the building. The third measurement for earthquakes is known as peak ground acceleration. This is probably the one that is more closely related to engineering work, but it's probably the one that the general public rarely discusses. Literally, this is a measurement of how did the ground accelerate by instruments that were installed in various locations prior to the earthquake. What you'll find as you look at these instruments is they're often categorized as what they are installed on. They may be free field, meaning that they're placed at a location which is relatively far away from any man-made structure, but more commonly they're on a building, maybe a bridge foundation or a dam. One of the things is this measurement is probably the one that's most closely related to how buildings are engineered and how we should design them to be more earthquake resistant. If you look at this map of Italy, it indicates with these triangles all the recording stations that made a recording from that earthquake. As you can see, they're quite extensively installed through Italy, and we had several readings from right here around the earthquake epicenter, but we also have readings very far away and even across on the other side of the Adriatic. In modern industrial countries, accelerometer instrumentation is becoming quite extensive. So like Italy, when an earthquake occurs, we get a pretty good recording of all the event. As we dig into this information, usually you come to a point, you click or you find an instrument. It usually has a station name, NRC, Norcia, oftentimes refers to the name of the structure that the instrument was installed on. Here it says what the local intensity was, intensity of 9, which means it was quite severely shaken. And then some information about the distance from the epicenter. And then we usually get 3 different readings of the 3 different components of that earthquake motion. So the instrument measures acceleration along a line. Usually these instruments are built so that they measure 3 different axes, including vertical, on how that instrument moved. So usually we get 2 horizontal readings, maybe a north-south and an east-west, and we get 1 vertical reading, maybe defined as the z-axis. PGA is the peak ground acceleration measured during that earthquake, oftentimes reported in percents of G, where a G is Earth's gravitational pull. So in other words, this one, we've got a reading of 38.5% of G, or 0.358 G, was the largest measurement of the Earth acceleration in this north-south direction. 1 G is 9.81 meters per second squared, or 386 inches per second squared. But what this is saying is that this structure had an acceleration about 1/3 of its weight in the horizontal direction. Now, of course, if we really got a reading in the north-south and the east-west, those are 2 components. And depending upon how the instrument was installed, the maximum acceleration probably didn't occur along either one of those 2 components. So if we do the vector sum of the largest north-south and the largest east-west, now we find that that vector sum is 0.53 Gs. So half the weight of the structure was trying to knock that building over. We also get a peak vertical acceleration recording. In general, the vertical accelerations are usually about 2/3 of the peak horizontal reading. Earthquakes just don't lift and drop the ground as strongly as they shake it side to side. So PGA going to be measured as a percentage of G. We also get a reading on the peak ground velocity, often reported in centimeters per second. Especially in the US, peak ground velocity is not used very much in engineering work. There are some countries where the codes are more focused on peak ground velocity, or at least have items that need to be checked. But in the United States, that hasn't been something of common use for our engineering work. Just as an example, I pulled up another earthquake in Myanmar the same year, only a few months different in time, which had a magnitude of 6.8, had a focal depth of 84 kilometers, only had 3 fatalities. In fact, this was in the same week as the one in Italy. So when you think about it, is having two major earthquakes in the same week so strange? I mean, is this an indication that maybe the Earth is becoming more active? Well, actually, there are about 100 earthquakes every year that have magnitudes of 6 or higher. So on average, we get an earthquake of a 6 or higher about every 3 days somewhere in the world. 2 or 3 of those earthquakes occur every week. The reality is the vast majority of them occur in areas with relatively low populations or in the oceans or in deserts and result in very limited impact on any community. In reality, it's quite rare that earthquakes result in fatalities and severe enough damage to actually alert the media and to have something that actually comes into the news. Thank you very much.